So we're going to get to the issue of talking about targeting gullies, but I'm going to give you a bit of a history lesson as well, because we're talking about the overall impacts of this whole NESP research program, and I want to take us back in time a little bit just to talk about where we actually were in 2015 in terms of our understanding and what we were focusing on then and what we talk about now. You've just heard a couple of presentations that sort of talk about how we've come a long way, and I think that's absolutely true, and that's in no uncertain terms due to the impact of this the NESP research program. And I think really what we're doing back in 2015, the most of the focus up to that point, particularly in terms of rehab, had been at that sort of, as Beck described, the small sort of scale gullies, which we would, and I'll talk about this in a sec, differentiate into the hill slope gullies and alluvial gullies, and there's quite a big difference. So they're not just big and small, they're actually hill slope and alluvial gullies, and there's a significant difference between them. By and large, we were dealing with these things as a sort of a grazing management type approach. We're doing some small scale stuff, and this is really important in terms of landholder engagement, but it actually, as we just saw from the talk that Scott gave, the dealing with those things was not really addressing the major source of the sediment from the actual gullies themselves. So there was a focus on low cost, but not necessarily meeting the reef targets, and we're going to talk a bit more about that later. So we have these two fundamental types of gullies, and I could give you another 20-minute talk on talking about how there's a whole lot of variations, but I'm not going to. But if we could just remember that there are these two fundamental types. So the sort of things that we've been hearing about are really targeted at those hill slope gullies, the grazing management, the small scale things. Those things do not address these big alluvial gullies, and that's what we need to talk about. Just briefly, the sort of work that we've been doing over the last 5 or so years has actually covered 5 separate projects, and we're going to attempt very quickly to give a rundown on the key findings from some of this work. We started out back in 2015-16 looking at some follow-on work from the previous Reef Rescue MetSurf work. I'll quickly look at that. NESP 2.10 was starting to canvass the idea of actually bringing mine-scale rehab type styles of work to gully rehab. 3.1.7 is looking at this in large-scale alluvial gully rehab. There's some work on gully classification. I'm not going to go into that in a lot of detail. And then there's also some work in Project 5.10, which is looking at gully mapping and the prioritisation work. And we'll go into that in a bit of detail. But just going back to 2015, so this is some work that was done in the previous reef rescue phase, but we continued it on in the early stages of NESP. And this was a plot scale study up on Crocodile Station, looking at how we can go about rehabilitating these sorts of alluvial gullies using regrading, reshaping and different surface treatments. And that work gave us some really good initial insights that we could get some pretty effective sediment reductions from doing regrading and surface treatments. And it looked like from that work that we could get something in the order of 80-90% sediment reductions from those sorts of treatments. But that was at a plot scale. So the key question then was, well, can we scale this up to whole large alluvial gullies? And this is where we needed to sort of think about really scaling things up. And so at this point, we had a workshop early on in the NESP program to bring together some industry people who had experience in doing mine site rehab, because it seemed to us that this was the sort of scale that we needed to be focused on to actually tackle this. So it's the right tool for the job to get these things done at the right scale. And so we started thinking about how can we do this at at large scale. And then, so in the next component of the NESP program, we then set about starting to do this scaling up. We started off with a bit of a small scale one. We didn't go right in the deep end. So this was the first site that was done at looking at a whole alluvial gully scale rehab on Crocodile Station. This was about a 0.6 hectare site, and we saw some really impressive results pretty quickly coming out of that. We then moved on, and I'm glossing over a whole lot of detail here. There's a whole lot of other people involved, and I apologise that I can't give due acknowledgement of all the involvement of these people. You're going to hear a bit more about this site in the next talk. This is a project done in conjunction with the Queensland Government, Greening Australia, at Strathalbyn Station. And this was really getting it to the right sort of scale. This was overall at this site, this was a site that covered something like 18 hectares of active gully erosion that was producing something in the order of somewhere between 8,000 and 10,000 tonnes per year of fine sediment to the reef. So this is the sort of thing that we needed to be targeting. So this was set up as a large-scale demonstration field experimental site. There was a lot of different gullies where different treatments were applied. I'm not going to go into that now, the detail of that, but just to give you a sense of the scale of what was done. Here's some of the results. We use this LiDAR differencing technique here to show both what was done in terms of the landscape reshaping, but it also allows us to measure the actual background erosion rates from the untreated gullies and then the treated gullies. And so this shows over a couple of years the different treatments that were done. You can still see there in the middle, that's our control gully that's still at that point untreated. That was last year. That site has now been treated as well. And what we found from that, and you don't need to read the detail in this table, but after 3 years of monitoring at these sites, and there's you can see there's a whole range of different gullies and different treatments within that overall site. But after 3 years, we're seeing the average rehabilitation effectiveness at that site was 98%. This was really beyond our sort of wildest expectations, really. We had a sense that we might get to some, fairly high numbers, but this was a pretty impressive result. One thing just to point out from that data was that the background erosion rates from those gullies before they're treated we were getting somewhere between 1/2 to 2 tonnes of fine sediment from those sites for every millimetre of rain that fell on them per hectare of gully. So through this rehabilitation program now, we've reduced that to about somewhere between 10 and 15 kilograms per hectare per millimetre of rain. So we're talking about at least two orders of magnitude reduction in the sediment load from these active sources. This is some other data which basically tells us the same thing. This is some of the water quality data. So there's a whole multi-factorial sort of monitoring program associated with this program. This is another set of data that showed this, the water quality data, again showing two orders of magnitude reduction in the sediment concentrations from that site. We're often also asked about, well, how resilient are these to major events? And we've got some insight from that from, this is the site at Crocodile Station in the Cape York, where these alluvial gullies back onto the river. And so when the river floods, these whole gullies go underwater. So you can see in that sequence there, this whole gully system was under about 3 metres of water. There was no effect of that flood on the stability of that rehabilitation at that site. So what have we achieved from all that work? So just to sum that up, what we've achieved at the Normanby site is overall about 165 tonnes per year fine sediment reduction. That was in 2019, so it's actually more than that now. And at the Strathalbyn site, currently it's around about 10,000 tonnes per year of sediment reduction from all of that rehabilitation work at that one site. Now, that actually equates to something like 1.2% of the water quality target, sediment water quality target for the Burdekin, and about 1.7 for the Normanby. At this point, I'm just going to hand over to James, who's going to carry on to talk about some of the other work.
Thank you. So as Andrew and Beck have mentioned, there's some real potential for remediating these large-scale sites. So now that we have that capacity, so what can we do in order to target the right gullies in order to achieve those water quality targets? So some of the things that we need to know in order to prioritise the gullies is where are the gullies firstly, how much sediment they're producing, the trajectories they're on, so in terms of their historical growth rates and how much they're continuing to grow in the future. Some of the context around and differences in gully types and the soil materials that those gullies are producing. Through our NESP research, we now have a bunch of this. We know where the gullies are. We have a really good constraint on how much sediment they're producing and methods to determine how rapidly they're growing. We need more ground truthing. There's certainly more repeat LiDAR data, and there's certainly some improvements to be made, particularly around investigating differences in relation to gully types, but we now know the scale of the problem. One of the key knowledge gaps is still being able to determine soil materials from remotely sensed data. So in terms of the mapping, we've developed methods and mapped close to 5,500 square kilometres of hotspot areas at a high resolution using 1 metre topographic data. So this is, as we've worked out, about 26,000 individual gullies have been mapped at both high and low yields, which equates to roughly around 5,500 hectares of gullied land. So from these gullies, we've been able to determine they're producing about an upper limit of around 240 megatons of sediment released into our waterways and the reef lagoon over their lifetime. So to put that into some perspective for you, it's a large number. That's fill up around a third of the Sydney Harbour, or about a third of the volume of Uluru, about 17 million dump trucks, 66,000 Olympic swimming pools, or 160 North Queensland stadiums. In addition to that, we've also mapped, so we've mapped in 3 catchments, mostly in the Bowen Broken Bogey, or Triple B, and Lower Burdekin, and then some smaller areas in the Fitzroy and Normanby catchments, and found distinct differences in the distributions of alluvial and hill slope gullies. So just for quick reference here, we actually broke hill slope gullies down into colluvial, which essentially have ample sediments within them, and rugged gullies, which are formed in steep, rugged terrain and likely on bedrock with shallow soils, so producing far less sediment. So in terms of the distribution of those gullies, we can see that in the Triple B, the hill slope gullies are dominating. There's about 55–60% of those gullies are hill slope gullies, whereas in the other catchments, the alluvial gullies are more prevalent. However, when we look at the actual sediment contribution from those gullies, in all catchments, the alluvial gullies are producing a disproportionate amount of the sediment in those catchments. I'll touch briefly on this. We've developed some new tools in terms of determining where the erosion is occurring and how much sediment is being produced. So we've been able to develop a method for determining the prior land surface using local terrain metrics and drainage lines to reconstruct the landscape prior to gullying, and that has allowed us to work out the volume of sediment that has eroded over the lifetime, and a potential active erosion index using topographic data to determine where within those gullies is actively eroding. And those areas we're able to use those areas to prioritise different gullies, which are the most active. And we've used that against measured data, used measured erosion data to validate those models and found that they're highly correlated. So both of these methods provide a basis for determining how much an individual gully is likely to produce in the future, which will assist not only with modelling gully erosion, but specific outcomes to on-ground prioritisation and effective targeting for remediation. So it's quite a big data set, so just going to run through some of the key findings from this research. So using those trajectories, we've been able to determine some of the backdate through the historical growth rates to determine some of the initiation dates. And we found two quite interesting peaks in gully erosion. So one about 130 years ago during the 1890s, and another peak of gullies that initiated around 75 years ago or in the mid-1940s. And these dates are really critical. This is in the lower Burdekin catchments. And so the 1890s is when sort of agricultural and land use change sort of began to ramp up. But in the 1940s, there was a real industrialisation in the post-war era, mechanisation, and increased land clearing. So it's really interesting that the gullies have fallen into those two time periods. By looking at those historical trajectories, we have observed some different patterns in growth rates. So as Scott sort of alluded to, a lot of gullies were initially thought to rapidly peak, and then slowly the yields would decrease over time as they approached the limit of their catchments. However, this really seems to apply mostly to hill slope gullies, and we've found some very different trends in alluvial gullies. So over that same time period, the sediment from alluvial gullies appears to either stabilise at a higher yield or continues to increase, despite having relatively small catchments. A lot of them have very small catchment areas compared to the size of the gullies. So it seems to be independent of catchment area. And that's largely due to an increase in exposed surfaces, so the subsurfaces in these gullies, and positive feedbacks in those erosion processes. Importantly, in those alluvial gullies, none of them have shown a deceleration in their growth rate. Another interesting component that we're really starting to appreciate is the effect of direct rain splash on those exposed subsurface soils. So we've sort of just recently finished a scoping study where we mimic the formation of pedestals. So these are things that we started to observe on the gully floor, so forming under ephemeral objects, things like gravel, cowpats, things like that, which suggests that they were forming very rapidly and they'd probably last for a season and then disappear. So we set up a bunch of erosion plates to mimic this process and left them out for the wet season, and came back after to assess how much the surrounding surfaces had worn down. So this is the kind of thing we saw. There's several up to about 10 to 25 millimetres high. Importantly, these pedestals represent they're a relic of what hasn't melted away. We placed them at locations isolated from overland flow, and this was during a significantly low rainfall year that this was occurring. And what we found is that across 11 gullies, it was generally an average of about 15 to 25 millimetres of erosion in those gullies across all the surfaces. So that equates to actually a very significant portion of the sediment yield coming from these gullies and suggests a greater non-linearity in the trajectories than we'd thought. So they're accelerating faster due to internal deflation and downwearing of those surfaces, and that's not easily accounted for because a lot of these, that rate of erosion is below the limit of detection. So it's not just about stabilising head scarps of these things. You can stabilise the head and it'll continue to erode at a very high erosion rate. So, for example, the gully with the highest yield here, an additional 1,200 tonnes on top of what was eroding from overland flow, actually had a bund diversion wall built around it, which had effectively cut it off from its catchment. And so that's quite something we found quite common, is that many of these alluvial gullies that do have those small catchment areas are still producing very high yields. So while practice change is very, very important, building a bund wall or just dealing with the catchment is not enough. We really need to deal with the surfaces in these gullies and treat them. So targeting the right gullies, so targeting the highest yielding gullies. Another really interesting find that we had was about 2% of the gullies are producing 30% of the sediment. And about 50% of the sediment is coming from just 6% of the gullies. So similar results, that equates to around 500 to 1,300 gullies respectively. And it really demonstrates that meaningful reductions can be achieved quite quickly by targeting these highest yielding gullies. We had similar results in the Normanby and Fitzroy catchments as well, albeit slightly different values. Of those high-yielding gullies, about 65% are those really big alluvial gullies. So again, those alluvial gullies are the ones dominating the sediment supply. But dealing with those alone is not enough. There's not enough of those high-yielding gullies to really meet the water quality targets. What we have to do is treat a bunch of smaller gullies at the same time. So the most cost-effective way to do that is to treat them all at once. So if smaller ones are left until later, they'll be far more costly and difficult to treat. And if they're not treated, then the targets just simply won't be met. So some research done in conjunction with NESP highlighted that focusing on those individual gullies won't achieve that, but significant cost reductions can be achieved and economies of scale by dealing with these as a cluster. So a group of gullies in close proximity together, consisting of both high and low yielding gullies. So that line there represents a 1-to-1 scale if we look at individual gullies compared to those groupings. And it found about a 2/3 reduction could be achieved long term if we deal with them as collectively. So there's already infrastructure in place. There's equipment on the ground, there's boots in the dirt. So without incorporating those gully systems, those moderate gullies will unlikely be cost effective in the future. So say for example, this gully group on the side over here. So the gully down below, on the southern gully, was producing about 1,100 tonnes, and the northern gully about 275 on average. And the southern gully was remediated and looks quite good, but the top gully has now been was decided not to be treated, and so it's unlikely that's essentially an opportunity lost. It's unlikely that we'll go back and fix that one, and it's currently this prioritisation work we've been doing creates essentially a treasure map of low-hanging fruits, and if we just deal with those low-hanging fruits rather than treating what's around them, we're not going to get there. So just to reflect on another insight we found by comparing with some other presence-absence mapping that's been done as well. And it's useful to compare the insights from this mapping work with those other data sets. So this other data set is now been completed, I believe, across the entire GBR catchment, and therefore likely to be incorporated into catchment modelling. So it uses essentially a 100-metre window and ascribes a simple binary presence-absence of gully erosion. So it's about 4 orders of magnitude lower than what we mapped. So we've downgraded our data to meet that and compared that data together. And it highlights some major disagreements between that data set and what we found. Now, it could simply, you might say, okay, well, they're just 2 different approaches, and who's to say which is right? But there's some real fundamental differences there. So if we look at overall, the accuracy was about 0.9. However, that's largely dominated by whoops, wrong button. The agreement in the no sort of areas with no gullies. Now, considering gullies affect roughly about 1% of the landscape, that finding is likely to be expected. So, but there's also distinct spatial, you can see on the map there, so over on the right there, the red is areas that we've mapped, that has been missed by the other mapping, and blue vice versa. So there's distinct spatial patterns in that mapping as well. And partly this is to do for a number of reasons. When we drill down and interrogate that, it's not just due to semantics, partly it's due to the different scales of mapping that were conducted. But there's some other things going on, and that's partly because this presence-absence mapping is excluding large-scale alluvial mapping, but also includes small streams and those steep bedrock rugged drainage lines. Now, the reason that's important is because excluding these alluvial gullies, for example, while they're dominating the sediment supply, if we exclude those, it's going to massively skew the yields that we derive and potentially completely derail the focus for prioritisation. So if those aren't in the data set. In terms of including small streams, so we can see in this mapping effort here, there's some small creeks. Now these are fundamentally different systems. So if those small creeks are being termed gullies and treated as gullies, it could lead to some serious issues. And same with these rugged drainage lines. So these are steep bedrock country. They're very shallow soils, and from our data, in the ones that were included in the data, they're actually the least significant part of the sediment yield in those catchments. So including these has the potential to really overinflate the yields from such features by orders of magnitude. And partly this is due to the conceptual model that's underpinning this. So in part, it allows ephemeral channels to be included in the concept of a gully. Indeed, the actual definition of a gully that is used in this mapping actually includes the term a small stream channel. However, it's not just semantics. These are really fundamentally different systems operating with different processes, have different sediment transport functions, ecological functions, and are managed in very, very different ways. So it's akin to stating that maybe a dry sclerophyll and rainforest are the same thing, which is just, we can't have that. So if this mapping was to be considered both gully and small stream data set, then it would be a really useful purpose. However, until those are disentangled, it's relying on, there's some potential serious implications there. Hand back over to Andrew.
Thank you. So I think we're just about out of time, so I'm just going to jump ahead to the conclusions. So look, I think it's pretty clear that we've now, we have all the key pieces of sort of the story together in terms of what needs to be done for gully management. I think one of the key things that's come out of the prioritisation work that James has just given you a brief overview of is that we're not going to meet the targets if we just deal with these, what we've called the low-hanging fruit. We're going to have to deal with some of these, what we would think of as lower intensity sort of gullies, but the best way to do it is in the first instance when we go and target one of these big active ones, you've got to do a whole bunch of other ones around it because that's the most cost-effective way to do it. So I guess, and then we have a major challenge on our hands in terms of this overall presence-absence mapping now to try and disentangle these, what's gully and what's stream, if we want to use that data set to actually help us prioritise and to help and to model these catchments and to use as a sort of useful data set going forward. So I shall leave it at that. And yes, just acknowledgements to the funding for this 5 years of comprehensive work, and we've had great fun doing it. Thanks.